Hello everyone, welcome back to my channel. In this video I will show you how to calculate the magnetic anisotropy energy using quantum espresso. And this video has taken me some time, not because the calculation is very difficult, nor is the procedure very complicated, but actually there are some bugs in this kind of calculation in quantum espresso that has not been resolved yet. So just before the calculation, I will briefly remind you something that you should keep in mind, that is here, that if you use newer version than Quantum Espresso 6.2, you will probably get a message in the non-self-consistency calculation saying that some spin components not found. Yeah, and if you see this warning in the output file, the calculation may make sense, but also probably it will give some nonsense result. And this is usually quite unstable depending on your system and also depending on your machine, a little bit random. So my suggestion is that you need to go back to Quantum Espresso 6.1, and then there is this spin polarization.dat file. I guess the whole routine of this magnetic anisotropy energy calculation was written based on this output file here. Yeah, so I would suggest that you go to Quantum Espresso 6.1, and then you will not see this warning anymore, and everything is stable. The second thing is that you need to use ultra-soft pseudopotential. You cannot use PAW, which is projective augmented wave pseudopotential. If you use PAW pseudopotential, sometimes you will get a crash in the non-self-consistency step, saying that the eigenvalues does not converge or something like that. Or sometimes you can get the program to run, but you get strange results. The energy depends on the spin angles drastically, like 10 electron volt or 100 or 1000 electron volt difference. That's just because the algorithm was not written for PAW. So you have to use ultra-soft pseudopotential. And also because usually this anisotropy energy is quite small, on the order of milli-electron volt, which is already quite large for this kind of energy. So you need to do careful convergence test over cutoff energy and also K-point density, because we want to resolve this tiny energy difference. So this is something that I want to mention beforehand. I advise you to use QE 6.1. You must use ultra-soft pseudopotential. And actually I found these messages from the internet here. Yeah, you see that in the mailing list. Actually you cannot do this with PAW. And the second thing is that, yeah, there's some error in the version of 6.2, 6.3, and I confirmed that 6.5 is also problematic. And then also here as well, yeah, you shouldn't use PAW. Okay, as the reminder beforehand. And then let's see what we want to calculate. So we have two sample systems that we want to show. In this video, I will show the calculation of nickel 100 monolayer. And in the next video, I will show iron 100 monolayer. And you know that for this kind of ferromagnetic material, it is a thin film. The electron movement will be constrained basically in plane. And if you add some spin orbital coupling, the spin will either prefer to point out or point in plane. And actually those are two very good examples, because for nickel monolayer, the easy axis is actually in plane. So the magnetic anisotropy energy is actually positive, but for iron monolayer, it is out of plane easy axis, and the magnetic anisotropy energy is negative. And actually milli-electron volt is already quite large for this kind of energy. And probably you remember that in the magnetism class, there is also some bulk crystalline anisotropy for nickel, for iron, for cobalt. But usually that is very small, around the order of micron electron volt, and this kind of calculation cannot resolve micro electron volt. Yeah? But this calculation is especially useful if you put some atom on the surface. The magnetic anisotropy energy could also be on the order of milli-electron volt. And for milli-electron volt, if you do the convergence test carefully, you can resolve it. And then, what is the general procedure? So generally, you have two steps to do. The first step is to do a self-consistency calculation to calculate the charge distribution. For here, we do spin polarized calculation, but a collinear one, which means that the quantization axis is along Z. And we use the usual scalar relativistic pseudopotential that you always use. Just remember that we need to use ultra-soft pseudopotential. And after this calculation, we copy the output directory to two new folders, basically copy the charge distribution from the first step and use it in the second step. So the second step is a non-self-consistency calculation. It uses the charge distribution of the ground state calculated from the first step, and then do a non-collinear calculation plus spin-orbiter coupling. So here you can change the direction of the spin. That's what it means by non-collinear. And then for spin-orbiter coupling, you need full relativistic ultrasoft pseudopotential. In this step, you can change to different spin angles, for example, pointing out of plane or in plane. And then in the output file here, you can find the total energy written in the tag E band. And then you can compare the E band of different angles, which means that you compare the total energy of different angles. The difference is actually the magnetic anisotropy energy. And optionally, you can also project the magnetic anisotropy onto different atomic orbitals using project WFC. If you are interested what is the origin of the anisotropy, like which orbital contributes to that. And now let's take a look at the input files. So first we calculate the self-consistency calculation, and it's basically here. As I said, self-consistency calculation, and this is the output directory. And we put the pseudopotential file in the upper directory, that is basically here, those two. We have to choose the ECUT WFC, this is the cutoff energy, and we can just see inside the pseudopotential file. And there is a suggested minimum cutoff for the wave functions, 75, and this ECUT WFC, and this is ECUT rho. So we choose it to be 80 and 500, and it's also the same for later use. This for relativistic one, just choose to be 80 and 500, and we set the verbosity to be high so that it outputs all of the bands on the K points, but of course this is optional here. And then the structure of the system is like we use IBROF 6, that is tetragonal. Seldim 1 is actually the lattice constant of FCC nickel, and to get that you can do first a variational cell relaxation as usual for bulk nickel, not for the monolayer but for bulk nickel, and you just copy the lattice constant here. But of course this is not really critical here, because anyhow this nickel monolayer is just an artificial system to demonstrate the anisotropy energy. And then Seldim 3 is actually C over A. The vacuum thickness is 5 times 6.575. So we have a thick vacuum to separate the monolayers, to let them don't see each other. And then we have two atoms in one unit cell and one type of atom, that is nickel, you can see here. And the two atoms, one is at origin and another one is 0.5, 0.5. So this is one monolayer on the 100 FCC nickel. Actually here I can show you the structure using X-crystal. Okay, you see that this is one monolayer of FCC nickel, and we have a thick vacuum spacing in between. Just as a side note, actually there is no FCC lattice in 2D. Maybe it's better to expand the number of units drawn so that I can clarify this more. Update, okay. Because you see this is a FCC lattice in 2D, however you can actually choose the unit cell in this way, yeah? And then you will get a square lattice. So in principle you can choose the square lattice in this way, just need to change the lattice constant to be 1 over square root 2 times the lattice constant now, yeah? And then we can actually further increase the number of units shown, so that you see that indeed we are calculating a monolayer of nickel separated by a large vacuum so that it does not talk to each other. And then we want to see that whether the spins wants to point out or point in plane. And then for the cutoff energy, we can find it in the pseudopotential, as I said before. And for the smearing, we use MP smearing, and this is quite good for metal. And then we choose a dGauss to be small, because we want the calculation to be precise. And spin equals 2 to start a spin polarized calculation. In this case, it is a non-collinear one. We have to start the starting magnetization. Actually, we need to be very careful about convergence, quite a high standard here, that's a small convergence threshold. And then we use the mixing mode of local TF because this is a highly anisotropic system. This will make it converge better. And we also lower mixing beta to make it converge better. And for the K point, because this is basically a 2D system, we only need one K point in the Z direction, but we need a lot of K point in the XY direction, and this is important. You need to test the convergence with respect to the K points. You need to increase this. Probably you need to go to 25 by 25 for the self-consistency step that we are talking here. For the non-self-consistency step, you need to go to 50 by 50. But for here, for demonstration, this is okay. We use 12 by 12 by 1. Yeah, okay. So that's the input file for the self-consistency calculation. And to run the code, we used this familiar line. And in this case, notice that I compiled Quantum Espresso 6.1. So we use 6.1, yeah. So I will not run the code here, but I can show you what is the output, basically here. But there's nothing special here. And after this, you need to copy the output directory to be these two new directories because we want to use it later. And we also don't want to destroy the previous output directory. So that's why we just copy it. In principle, you don't need to copy everything because what we need is the charge distribution and also the spin polarization. So you don't need a wave function, but in the end, for simplicity, you just copy everything that will work, yeah. And then for the second step, that is the non-self-consistency calculation, I can show you the input file here. Non-self-consistency, here we change the output directory to output directory X. That's the one that we copied from the first step. And then we need to set verbosity equals high here. This is necessary because otherwise there will be too many K points and there will not be any output of the energy that we want. So remember to set it here. The structure is the same and we need those lines here. So this means that we use spin orbital coupling, and this is to set non-collinear magnetism to be true so that we can change the direction of the quantization axis. And this is also necessary because we want to start from a collinear spin polarized calculation. So this basically rotates the collinear linear calculation to the quantization axis that we set now. And we set no symmetry to be true, and this is also needed. And then we need to set the spin angle. So the first angle is actually the angle between the spin and the z-axis. And the second angle is the angle between the projection of the spin onto the xy plane and the x-axis. So this line means that the spin points to the x-axis, and we label it here in the input file name. This line means that the spin points to the z-axis. So restart mode from scratch, just to mention, means that we don't start from the wave function because we just want to start from the charge distribution. And we explicitly write here that we start from the charge potential charge distribution, basically from this output directory. But this is also optional because this is by default set to be so for a non-self-consistency calculation. This is the diagonalization threshold, and we also set it to be quite strict because we want to resolve the tiny energy difference, yeah? And then we need to change the pseudopotential file to a full relativistic one, yeah? This is important, otherwise this doesn't work. For all of the others, it's the same. So if you are familiar with VASP, probably you know that they recommend that you double the number of bands in the non-self-consistency calculation in this case. But in Quantum Espresso, it is automatically taken care of, so you don't need to do it. And we run the calculation by this line here, very similar to this. We just change the input file. I will not do the calculation here. And this is the calculation when the spin is pointing in the x direction. Let's take a look at the output file. And we start from the beginning. Everything is quite similar as before. Maybe I make it larger. And let's scroll down here. If you have the warning that they cannot find some of the spin components, we will find it somewhere here. So after the K point and before the actual output for the calculation. So here we don't have anything, so we don't have that warning. And then just search E band And this is the important value here, yeah? And we just copy it and paste it here, yeah? EZ minus EX in the unit of electron volt. We basically copy the file here and just comment out the first line, use the second line, which means that now we calculate the case when the spin is oriented along the Z axis, and we label it also in the name of the input file here. Everything else is the same. We also need to change this output directory to be Z. Okay. And then we use this line of code to run the calculation. And this is the output file here. You should check whether there's any warning. If not, you can find where's the E band here. If you cannot find this line of E band here, you have forgot to add the verbosity equals high line in the input file. Yeah, just add it, and then there should be this line here. So we copy and paste here, yeah. And remember that in this case we have 2 atoms in a unit cell, so we have to divide it by 2, and then it is EV per atom, yeah. And then the result is actually 1.075 milli electron volt per atom, and this is actually consistent with the literature. But of course, if you really want to get a really nice estimation, you need to do a convergence test. And I suppose this 1.2 is also a rough idea. It is also not really converged. So now it is actually done if you want to just calculate the magnetic anisotropy energy. But if you want to do more, there is actually an additional step that you can project anisotropy onto different atomic orbitals to discuss what is the contribution from different orbitals. And for that, let's take a look at the input file for this project WFC. It's important that you specify the output directory because we want to fetch the data from the previous steps, and the prefix should be consistent, and the minimum energy, maximum energy, you can specify it, you can leave it out. And this energy resolution and degauss we use as before. Ngauss equals 1 means this MP is mirroring that we used before, so it's also consistent. The output file is encoded here, and for the Fermi energy, actually you need to find it in the output file of the last step. I can briefly show you here, and it's basically here, yeah, this is the Fermi energy. Just copy and paste here. And you also need to set this to be true. There's a similar flag as we did in the second non-self-consistency calculation step. And to run the calculation is actually very simple. Just use this line of code here. It should be fairly fast. And then also for the case where the spin point to the Z direction, we need to specify the output directory for the Z direction. And everything else it's similar. We change a different name for the output, and we found the Fermi energy from the output file of the Z direction calculation. And this should also be quite fast. What you can see in the output file here is that it actually write everything down in different orbitals, yeah, and then you can analyze the file. But this is beyond the reach of this video. But for simple magnetic anisotropy energy calculation, you just need those steps here, yeah. Okay. So in this video, I've shown you how to calculate the magnetic anisotropy energy of nickel 100 monolayer, and it turns out to be in plane easy axis, and the magnetic anisotropy energy is around 1 milli electron volt per atom. And in the next video, I will show you the calculation of actually the iron 100 monolayer. So if you learned something from my video, I really appreciate your like or subscribe to my channel, and I hope to see you next time.